You can hear me. Thank you very much for joining me. So let me first introduce the laboratory for which I work for. Maybe you have seen it from other colleagues, but from the ones that haven't heard about it, is the European Laboratory for Nuclear Research. It's located in Geneva and has more than 60 years. The key aspect of CERN is collaboration, and there are more than 20 different countries and hundreds of organizations collaborating to make this work, and we are very proud of that. So what do we do there? We are trying to answer very fundamental questions about physics. What are the particles made of, dark matter, how all the universe was created, and so on. And this is the slide about mine is bigger, and this is how we are known by, and it's a particle accelerator that is underground. It has 27 kilometers, and is the largest machine in the world. Is the fastest racetrack because we accelerate particles reaching almost the speed of light. It's the emptiest space in place because where the particles are being accelerated, there is nothing else inside. So we just collide what we are interested in. And it's also the hottest spot on Earth because where particles collide, a lot of heat is generated. But getting close to the topic and to IT, what I'm presenting today is a Spark job implemented and integrated with our monitoring infrastructure. So at CERN, we have a team in the IT department which is dedicated to anything related with monitoring. And the infrastructure that they have deployed looks something like this. You most likely have seen something similar before. We send all the data to a message broker, in that case Kafka, through a gateway which is built out of Flume agents. And then this data goes out to, again, using Flume agents for archiving to HDFS, to Elastic for greping and basic visualizations, and to Influx, where we do some more complex plotting using Grafana. But what you can see is that in the middle, from this message broker, we can plug streaming jobs, and this is what I'm doing. So I've developed a job, a Spark streaming job, which basically look at the data that we are sending and spot anomalies. And I'm specifically looking at the data that is sent from the tape storage infrastructure, and I will talk more later about this. But in order to understand how it has been implemented and the different parts, there are different abstractions that you should know about. So these are different components that you can, let's say, extend easily. And we have metric source, and one metric source is just a Kafka metric source. But the source, let's say the data coming from Kafka is basically bytes, so this needs to be understood. We send data as JSON, but from JSON to metrics, there needs to be some parser and some way to understand how to translate the data being sent to Kafka. And for that, we have a component which is called the schema, where you specify from where to extract the attributes of the metrics, from where to extract the value and the timestamp. Then you can apply some aggregations on this data. So for that, we have some aggregators, let's say. And then metrics coming from this schema or from these aggregations are filtered and analyzed by a component which is called monitor. I will go in details through the different components that build the monitor. But the idea is that you do something relatively complex there, the analysis, and then these analysis results are sent to an external storage where we can plot what is happening within this analysis. And then out of this monitor, actions are triggered, and these actions are performed in components that are called actuators. It could be like sending an email, running a random job, something like this. So the monitor is basically built by different components. One of them is basically a filter. We filter by the attributes of the metrics that are going through the Spark job. And basically it says, okay, we want to analyze the metrics of a certain characteristic of our infrastructure in a certain way. For example, all the CPU, so we filter by all the metrics that represent CPU usage in a specific way. Then we have the analysis. Every single metric that passed the filter is analyzed. And how it is analyzed, it depends on the analysis that you configure. And there are analyses as simple as a threshold, where you configure the value through which this analysis would produce a warning or an error. Or you could have something a bit more complex, where you could compute the average and the standard deviation, and you get some thresholds that are learned depending on the recent behavior of the metric. Or you can do something more complex, which is a metric that has a pattern, but you may notice that there is a moment when this metric doesn't keep repeating. So the analysis learns the pattern that this metric is following and detect the anomalies when the metric goes out of the thresholds that are computed. This processing is very simple. You just expect the same to happen in the same minutes of the next hour, and that's it. It's something very, very simple. And then you have the triggers, which is the component that decides when an action is triggered, because you don't want to trigger an action every time that your metric goes out of the thresholds, because then it could be very noisy, but you want to trigger it probably after some time. And this is the case, for example, for a trigger that is called constant. So it's basically you configure how many minutes and in which state you are looking for. So you can say, for example, if the metric has been in a status error for 20 minutes, just raise 13 alerts. But you can go for something more complicated, and you can go for a trigger which basically take a percentage and also a time, and because it can go to OK and then error, and it can flip from statuses. But if 80% of the time, for example, is in warning and error, you want to get notified, you could configure this in that way. OK, so all these components are configured from the machines which are producing the metrics. And I would like to explain to you how this configuration flows from the machines where we actually have the tape drivers to this Spark job running in our Hadoop cluster. So basically, the changes that we do in the configuration flow are sent to a synchronization service. And to this service, ExDeMon is the tool is subscribed. So any change that is produced in this configuration is, let's say, taken by the Spark job. Now, all these components, this is a distributed processing, so you need to have all these components in all the workers. So as soon as they are needed, you can take the required component out of all of these. And so each worker keeps a list of all the available components that they have been configured, and they, depending on the data that is flowing, they are used or not. What tools are behind this? Well, we configure the machines. The configuration management of the machines are done with Puppet. So you configure in Puppet, in ERA, the different components. These changes are pushed to Zookeeper, that is the synchronization service, the tool that we have for synchronizing this configuration. And then the job gets subscribed to every single change that is produced in Zookeeper. How the configuration looks like? Well, what you can see in Puppet is basically the declaration that you have in your manifest. For example, there I'm declaring a monitor, and then I declare the different components within a monitor. Because it's a monitor, if it would be an schema, it would be obviously different. But for a monitor, we had filter, analysis, and triggers. So there I'm specifying that this monitor should monitor all the metrics from any hostnet that are reached bytes per second. And the type of analysis that I'm applying is season. And the season lasts 1 hour, and then I put the different triggers that I want to use and their configuration. What is Puppet running behind is Zookeeper CLI. That's a project that is helping us to push the configuration. It's an open source project that is helping us to push the configuration to Zookeeper without us implementing any library or client. And then with Zookeeper Zoo Navigator, which is again another open source project, we can see on what is stored on Zookeeper, and in that case, it's the JSON that represents what we have configured in Puppet. Once this is configured, the Spark job produce the result, because what the configuration that you are putting there could be wrong. Or there could be some problem with the configuration, or the job is not taking the configuration. The result of configure is such the component goes back to Zookeeper, so we can see that the component is available and well configured. There is also, this is a web interface, but there is also a command line interface to see if any of the components that you configure has any problem. With the components that I mentioned, there are different configurations that you can do. This is just straight as I mentioned them, but you can have different sources, and each source would have different schemas, or you can have different aggregations, and the actions that are thrown by this pipeline could go to different actuators. So, for example, you run a runtech job and you just send an email or something like that. Now, this first has been implemented using Streams API, and now we are trying to move the implementation to structured streaming. But we have found some difficulties in this implementation, and is what I wanted to share here. For example, the status that you save in structured streaming cannot be queried, or this is my understanding. Before, you could just call a state snapshot and get the current statuses that are there. This is useful for us, for example, because if you don't know the query of the status that is stored there, all the attributes and all the status, the key of the status that is stored there, you cannot access it. And we would like to do that, for example, if we remove a machine and we want to say, okay, forget about everything that was coming from this machine and don't throw any alert. That's something that we cannot do without that. Then another thing is that for every single monitor that we put in place, we would have the plan was to have a streaming query, a structured streaming query. The problem with that is that every single query would need to be would need to read all the data from Kafka several times, let's say all them in parallel, and this could be a problem. And this would happen because we consider that we don't want to stop the job and start it while it is running, and we want a new configuration of a new component. We want this to keep running. So the idea is that you configure a new component, or you modify the configuration of a component that is running in a query. So you stop the query, start it again with a new configuration. And then another problem is the combinations of different output modes and queries that you can do. You need to be very careful. You need to be careful when you configure when you change the different components and they are not compatible with the output mode or things like this. Now, especially since we started the development of the job, we have been losing continuously the status that we are saving in the checkpoint. So what we are doing is moving the status to an external storage, in that case, Kafka, and when we delete this checkpoint every time that the checkpoint saved on HDFS every time that we start the job, and we load it from Kafka. How the basic idea is that you have a topic which log compaction configure. So such configuration allows you to store values for keys, but no, let's say you overwrite previous values that you have from the same key. We store all these key values as JSON, and once you start the job, you load all the data that you have in this Kafka topic. Now, you need to continuously keep updating the status in the Kafka topic. So in every batch, the keys, the values that have been updated needs to be sent to Kafka. I mentioned in the title of my presentation Markov, so here it is. Markov, you may have heard about him during your studies, and it's basically an stochastic model to describe events in our case in systems. And the basic idea is that a next event depends uniquely on the previous status of the system. The simplest version of a Markov chain, and it can be easily understood with the weather, is when you have the probability of one status to go to another one, and this can be understood easily with, in that case, the weather. So you have a matrix of probability from sunny to cloudy to rainy, and what is the probability of the next day to stay in the same status, in the same state, or in a different one. But this can get a bit more complex, and you can have something that is called hidden Markov models, because the previous change that I saw, every single status can be observed and can be seen, but this is not always the case. Normally, you have a system which complete status cannot be observed. So there is something that is called hidden Markov model, where you have a hidden status and an observable status, and you have the probabilities of let's say, observing the status which is inside, and the probabilities of moving from one status to another, which is a bit more complex, but with the time that I have, it's more complex more difficult to explain. But still, you can complicate this a bit more, and the probabilities from going from one status to another doesn't need to be constant, but it can be distributed a long time. So depending on the time that is moving from one status to the other, you can have some probability distribution in order to try to predict when your system is going to move from one to another. Now, why I'm explaining Markov chains is because we are trying to apply this model to predict failures in the tape infrastructure at CERN. What is the idea? Well, tape storage is basically a robot which, when we request a file, goes to the tape which has this file stored, grab the tape, bring the tape to a driver, put the tape in the drive seek to the position of the file, read it, and then when it finishes with the tape, it takes the tape and put it back in his position. Now, there are transitions here. And any of these steps could fail or could be successful, or the whole session could fail or could fail in an earlier stage. These are transitions that we can model with Markov chains, and specifically with hidden Semi-Markov model, we want to do it. We are doing that in collaboration with one university in Madrid, Universidad Autónoma de Madrid. And all these events are coming from the logs of the drivers that are reading, are managing these tape libraries. The data is labeled. We know what happened. We can learn from that. We learn which are the failures and the errors. And yeah, that's work in progress. So I couldn't bring you more results, but instead of that, I can tell you something about HTM. This is, probably you haven't heard about this, but this is a new way of understanding how our neocortex work. HTM stands for Hierarchical Temporal Memory and was first described in the book on intelligence in 2005, and they tried to follow as strictly as possible the new discoveries in neuroscience. It's based on two principles. This is not deep learning, but it shares some ideas from it. And one of them is hierarchy. So it comes from the principles that we understand the world in a hierarchical way. So our hands are made of fingers, our fingers are made of skin and nails, and so on. And another important aspect is that it understands the way of working as predictions. It understands that our neocortex is constantly doing predictions. That's why it explains the amount of connections that we have as feedback in our brain. And a way that I like to explain this is when you go down on stairs, you are not actually thinking about how you move your legs and how you are stepping down or up. And this is why, and this is because when you step down, your brain is making the prediction that you are going to touch the next step. If you touch it, your attention is not gathered and you don't need to think about that. However, what if you miss a step? All your attention is gathered there. And why? Because the prediction that your brain did was not correct. So this is the basic understanding of how HTM understands how our neocortex works. And this has been integrated with the tool that I described before as an analysis within the tool. This understanding and this theory, let's say this methodology has been implemented in Java and in other programming languages. But for Java, there is a library on GitHub that is basically htm.java, the name. And there, I would say there are many parameters to tune there, but still maybe the biggest problem that we have got is how to serialize the status of this, let's say, network that is making use of. You need to save the status between batches because you want to remember what happened before. The implementation of this library has been thought for such a thing, so it's well implemented, but still we need to write some adapters for Creo, which is the serializer that we have in Spark. And also, since we are storing this data into Kafka as JSON, we needed also to parse this to JSON, but the first trick and what is working for us now is basically parse it to bytes with an internal implementation of serialization library that it comes with. Now you come with a very long array of bytes, so we parse it to a base 64 string, and then this goes as JSON. So you cannot see anything there, but the status is kept, and this is how we keep the status moving from one batch to another. These are some results. What you can see here is not very spectacular because this can be just detected with a threshold, but still it learns what are the new patterns, and we expect to do more with that. So you can basically input in this network also other metrics and raise some actions if this behavior hasn't been seen before. Conclusions. The use of Spark at CERN is increasing. You may have seen some other presentation from other of my colleagues, and this is also the case for monitoring. We have deployed a monitoring infrastructure that make use of different mechanisms for raising alerts, but if you want to do something relatively complex, we have the option of Spark, and this is what me and some of my colleagues are going for. Markov models, well, I expect to have results soon, but unfortunately I couldn't bring you much about that. The basic idea, what is our plan, what we plan to do. But however, I bring HTM as a promising anomaly detection mechanism, because actually the whole theory and the whole idea is about anomaly detection. Our neocortex is expected to do predictions, but if they are not met, anomalies are detected. This is like the whole theory about that, and is fitting very well in a monitoring environment where you want to detect prediction anomalies. And that's all from my side. If you have any questions, they are more than welcome.
Any questions?
No?
No?
Then easy.
Oh, right here.
Thank you. I just wanted to understand, you said filter, right? How can you even thought of like thinking of filter before you look at the data, analyze it? First you said filter and then analyze, right?
Well, the thing is that you are receiving all the metrics that we collect there. We know the data, we know what we are sending, and when you declare a monitor, you want to apply a certain analysis only on a specific subset of the data that you are sending. Each type of data that we send has different behaviors, so it depends on the behavior that it has, or how you want to detect anomalies, that you apply a different analysis. How you apply a different analysis to different subsets is there by specifying a filter, so you allow only a certain subset or certain type of your metrics to go through, and then you apply the analysis that you want only to this subset of your data. Okay.
As far as I understand, your approach is you're updating the state when new data arrives. Is that right?
Yeah.
How do you ensure that the data is receiving or is received in order? Or isn't that an issue in your setup?
Well, in principle, you don't ensure that. Normally, what you have in some of the stages is that you discard data that is, it comes with a very long delay. Otherwise, there are. It is expected that some metrics doesn't come in order, and they are taken into account. Before the late metrics arrive, you are producing results that are not doesn't represent the reality. Let's say. Yeah.
Any other questions? Okay. Thank you, Daniel. And please remember to rate the sessions afterwards. Thanks.
Thank you.